Right, we are going to start a new lesson in chapter 11. It's 11.4, and it's all about how to use radicals in geometry. So we've been learning about radicals or square roots, and we're going to start a little section this week and next week on how some of the ways that you can use square roots in real world. Okay, so this first one is all about the Pythagorean theorem. Before we get into what that theorem is, we got to talk a little bit about geometry, specifically right triangles, because the Pythagorean theorem only works for these special kinds of shapes. So first of all, what is a right triangle? Well, I have some examples here below, but right triangles are triangles, three-sided shapes. And specifically, this word right means that you have a 90-degree angle. So in this case here, I'm going to take a look at my first triangle here. This is a 90-degree angle. And I can tell that because they're using this symbol. It looks like a square box. And 90-degree angles, you see everywhere in real life. In fact, you probably see it around your room right now if you just look up. Your piece of paper has 90-degree angles for all the corners, right? Yeah, there's all sorts of things. The table has corners that are 90-degree angles, and so on and so forth. So anyways, in a drawing, we know something's a 90-degree angle when they have this symbol here. It looks like a little square. For this triangle here on the right, this is the other 90-degree angle, okay? Because again, you can see the little square symbol. All right. There's other parts to the triangle that I do want to point out. There's names for all the different sides of the right triangle. And I'm going to start off with the two sides that are making up this 90-degree angle. This side here, right, I'll highlight it, and this side here. These two side lengths are called the legs. Like you have two legs that you walk on. This is one of the legs, and this is the other leg. Actually, I guess I should say leg, single. So there's two legs in your right triangle. Now, the legs are not always equal. Sometimes you have ones that are longer than the other. Sometimes they are equal. It just depends, okay? And then the last side, the other side, this third side, which I'll highlight in pink, this is called the hypotenuse. This is an old Greek word, hypotenuse. Hypotenuse, okay? The hypotenuse is actually the longest side in a triangle. Another thing that helps separate the hypotenuse from the legs is, can you see how the hypotenuse is opposite of the right angle? That's how I know we have a hypotenuse. You see it's opposite of the right angle. Whereas the legs are the two sides that are attached to the right angle. They make up the right angle. You guys see that? In this case, for these triangles, we call these the legs, and that's the hypotenuse. But we also use these variables in math. The hypotenuse is identified by the letter C. And that's going to come in handy later today in our Pythagorean theorem. And then the two legs they use the variables A and B. Now, does it matter which one is A and B? Not really. Usually you go the smallest one, A, and then the next biggest one, B, but it doesn't really matter. I can call this leg B and this leg A. It doesn't really matter. The two legs can be interchangeable, okay? But the one that has to always be C is the hypotenuse. Again, the hypotenuse is opposite of the 90-degree symbol. So sometimes you have triangles like this one on the right-hand side that are flipped or upside down or funky, right? So this is why it's important that you understand which ones are the legs and the hypotenuse. I'm going to start with the hypotenuse because that's the easiest to identify. This is the hypotenuse, and I can tell that, again, because it's opposite of the right angle. And I know these two sides here, oops, wrong color. I know this side here is one of the legs, and then this side here is the other leg. I know that again because these are the two sides that are attached to the right angle. Again, which variables do we assign these? The legs, we use A and B. The hypotenuse is always C. So there's some right angle vocabulary for you. It's important you understand the vocabulary and the different parts of a right triangle. And you'll be using this in Geometry 2 next year as well. Okay. So anyways, Pythagorean theorem uses the right triangle. All right, what is the Pythagorean theorem? First of all, Pythagorean theorem. And the Pythagorean theorem only works for right triangles. And it's this. This is the Pythagorean theorem. It goes a squared plus b squared equals c squared. It's this formula right here, and this formula is called the Pythagorean theorem. You may or may not have heard of it before. Okay, a squared plus b squared equals c squared. And again, where do the a, b, and c come from? Those are our legs, right? So again, here's this right triangle. Remember, this side here is one of the legs. This is another leg. And again, what do we call this side? The hypotenuse. And A and B are my two legs. The hypotenuse is C. So what we're doing is we're taking one of the legs and you're going to square it, right? Same thing here. You're taking another leg, whatever number that is, and you square it. If you take those things and you take those two numbers and you add them together, they're actually always equal to whatever the hypotenuse is. I'm just going to abbreviate. Squared. It's pretty amazing. Any right triangle, any size right triangle out there, if you take both the legs and square it, it's always equal to the hypotenuse squared. So if you go on and take a tape measure and do this, you'll see it works. Okay? But how does this help me, right? What are we going to do with the Pythagorean theorem? What we're going to be doing with the Pythagorean theorem is helping us solve some of the missing side lengths of a triangle. Because, and I wrote it down here, if you know two sides of the triangle, then you can solve for the remaining side. And this is going to help us with a lot of different things, construction, if you're going to go into engineering or even drawing some of these things, designing shapes, designing anything. Pythagorean theorem will come in handy. Okay? Okay, so this equation, a squared plus b squared equals c squared, that's the big key concept for today. And we're going to talk about how we use it. So, first example. What we're going to do is, let me zoom out here so you can see the entire direction. We're going to find the missing side length. Our answer should be in simplest radical form, and we'll talk about what that means as we go, okay? But as you can see in this example, I drew a right triangle. See how we have a right angle here? I can tell it's a right angle because of that square symbol. And we have one of the side lengths is 8 inches. We have 15 inches here, but we do not know this last side. That's why we put an X here. So my goal is to figure out how long is this side of this triangle, okay? So when I do this, what we're going to be using is my Pythagorean theorem. So let me zoom in, which is a squared plus b squared equals c squared. Now I need to identify what is a, b, and c. Just like before, we have this right angle, meaning these two sides here should be the legs. And remember, the legs are a and B. And the hypotenuse, and I know it's the hypotenuse because it's opposite of the right angle. This is the hypotenuse. I'll abbreviate hypotenuse. But remember, we used the variable C to represent the hypotenuse. So we've got the legs A and B, and then the hypotenuse is C. Miss Lee, can I change A and B? Can this one be A and this one be B? Yes. Again, the legs can be switched, but the hypotenuse has to always be C. So A and B can be switched, but C is always the hypotenuse. So anyways, what I'm going to do is I'm going to take these values and we're going to plug it into my Pythagorean theorem, starting with A, right? So what is A? If I look at my picture, I decided to label A 8 inches. So I'm going to replace A with 8. So this will be 8 squared plus B. In this case, B is 15. So I'm going to say 15 squared. Don't leave anything out. Equals C squared. So again, C, we don't know what it is. And in fact, they use the variable X. So I'm going to replace that with X squared. And there we go. I've replaced B and C with what I have in my drawing. Okay, from here, I can solve for X. I'm going to use my order of operations. I see we have 8 squared. That's 8 times 8. That's 64. I know that one. And then 15 squared. And some of you guys may know this off the top of your head. If you don't, grab a calculator. We'll go 15 squared, 225. So 15 squared is 225. There we go, equals X squared, like that. I brought down my X squared, and then look at how I can combine these two like terms. This is 64 plus 225. If I add them, I get 289 equals X squared. And then I'm not done. I need to solve for X. Now, think about, just like we practiced last week, how do you get rid of a square? How do you get rid of this exponent 2? And we get rid of it by taking a square root, right? The square and the square root cancel. Whatever I do to one side, we do to the other. So this is why we practiced solving equations last week, so that we can use it in areas like geometry. Okay, so I gotta figure out what that is, right? The square root of 228. Actually, since I have a calculator, let's see if 289 is a perfect square. So again, I'm going to go to my calculator. Let me see if I can do this on the screen. Oh, there we go. Let's see. For a square root, that's this button here for me. I'm going to click it. The square root of 289 is equal to, I'm not using my calculator correctly, 289 square root is equal to 17. Hey, it's a perfect square. Let me just double check that. 17 times 17 is 289. Hey, what do you know? It's a perfect square. Cool. So this 289 actually simplifies into 17. And there we go. We found the missing side. If I go back to this picture, I know the hypotenuse is 17 inches long. So this is kind of cool if you were actually going out and let's say you had to you had to go build something, a right triangle specifically. You know that missing piece of, let's say you're doing wood shop in Mr. Borgiali's class, you need to know how long that piece of wood needs to be. It needs to be 17 inches long, right? So it's kind of cool that you can use these theorems. Okay, so there we go. It turned out to be a nice whole number. Okay, let's do another problem. Number 2. Oh, words. Word problem. Okay, that's fine. Let me read it. One leg is 4 feet, and the hypotenuse is 5 feet. Find the other leg. Well, you know what's going to help is if we draw a picture. So it doesn't really tell me how to draw the picture, so I'm going to draw whatever triangle I want to. But since we're talking about Pythagorean theorem, I know this has to be a right triangle. So here, I'll make this my right angle. So we draw a right triangle, right? This is nice and perpendicular, this 90-degree angle. Okay, I'm going to label some of my information. So it says one leg is 4 feet. So I'm going to go to my picture, and one of the legs is 4 feet. So here, 4. And then they said the hypotenuse is 5 feet. So remember, the hypotenuse is opposite of the right angle. So, right, this is opposite of the right angle. So this hypotenuse is 5 feet. Find the other leg. So that must mean we don't know what this side is, this other leg. So I'll put an X here since we don't know what it is. And there we go. We're ready to start my Pythagorean theorem. I need a squared plus b squared equals c squared. So remember, a, b, and c, the legs are a and b. So this leg is a, this leg is b, and then the hypotenuse is always c, a, b, and c. So I'm going to go ahead and plug things in. A, I can replace with x, so x squared, plus, or b, look at my picture, that's 4. So we're going to say 4 squared is equal to, and c is 5, so 5 squared. Okay, so take a look at my equation. Now that I've plugged in the numbers, we're going to go ahead and solve it. We have x squared. Can't do anything with that. Oh, here, 4 squared. I know 4 squared, that's 16. So I'm going to replace this with 16. So I can go ahead and write 16 here. We'll bring this down. And 5 squared is 25, 5 times 5. And there we go. I can All right, so now I'm trying to solve for x. And let's see, I need to get x squared on its own. So how could I do that? Well, here, 16 and 25, I see these are like terms. We can combine them by moving it to the other side. So that's what I'm going to do. I'm going to subtract 16. There's the equal sign there, right? So I have to subtract it to get it over to the other side. When I do that, this cancels. Let me bring down x squared. And 25 minus 16 is 9. And there we go. We're almost done. How do I solve for this? I'm going to square root both sides. So that way the exponent, the 2 and the square root cancel. So we're left with x is equal to, the square root of 9 is 3. And there we go. That means x is 3. When I go to this picture over here, I know this side length is 3 feet. Cool. There we go. Okay. All right, so square and square root, they cancel each other out. So that's what we're doing. We're solving some radicals here. Next question is another picture. I'll give you guys a moment to take a look at this picture. It's a right triangle, I see, because I see a right angle here with that square symbol. I also see that we have some sides labeled. Let's see. I like to always identify. With my right angle, the 2 sides attached to the right angle are the legs, meaning I can call the legs A and B, like that. The side that's opposite of the right angle is called the hypotenuse. See this hypotenuse here? Do you remember what letter we use for the hypotenuse? That's right, it should be the variable c, the letter c. And then we have a squared plus b squared equals c squared. And this works because I have a right triangle. All right, so I'm going to do that. We're going to say a squared plus b squared equals c squared, the Pythagorean theorem. And we're going to plug in the values from the picture. See, a is 10, so I'm going to say 10 squared. B, we don't know, it's x, it looks like, so I'm going to say x squared here. And c is 18, so 18 squared. Okay, I'm going to go ahead and multiply some things out. 100, 10 times 10, plus 18 squared. You know what? I'm going to go to my calculator. So let me go to my calculator. Let me clear. So 18 times 18, or 18 squared, 324. Okay, so I'm going to go back to my work. 18 squared is 324. All right, let's continue to solve for x. I can subtract 100 to the other side, because again, my goal is to get x by itself. So this is 100, so I'm going to subtract 100. I'm left with x squared is equal to 224. And how do I get rid of an exponent 2? A square? We square root. Square and square root cancel out, right? So these two things cancel. I'm left with x is equal to the square root of 224. You know what? I wonder if that's a perfect square. Let's go to the calculator and see. 224. I'm just curious. So if I type in 224 and I square root it, ooh, the square root of 224 is not a nice whole number. Okay, so it's not a perfect square. Darn it. So what I'm going to have to do then is simplify it. Now remember how we did that in the last section, simplifying square roots. I need to figure out something to split this into. What times what makes 224? And I should be using my perfect square numbers. Remember the perfect squares? 4, 9, 16, etc. The whole list of those. We should see if 224 can be divided by any of these numbers. In fact, I'm going to start by trying 4. So if you have your calculator, you can try it out. What if I take 224, let me clear this, 224, and let's see if it can be divided by 4. I'm going to hit enter, and it's 56. You know what? I know that I can split 224 into 4 and 56. And then we can continue simplifying from there. But you know what? I wonder if I can go bigger than 4, right? That way I can do this in less steps. I wonder if I can divide it by 16. Let's try it. Let me grab a calculator again and see if 224 can be that was way too many numbers. 224 can be divided by 16. Let me hit enter. 14. That's so much better because 16 and 14 means I have less steps to do. See, 16, the perfect square, isn't that a whole number 4 when I bring it down? And then the square root of 14, can I split that up any further? No, not really, right? I can't divide by 4 or 9. It doesn't split up any further. So this is 4 times the square root of 14. X is equal to this. And that's what I mean when I said earlier in my directions to leave things in simplest radical form. So we are not rounding, right? You are not doing decimals. So you're not going to get a decimal. So for those of you guys who are taking this and saying x is equal to 14.9, we're not doing that right now. I want to leave my answer in simplest radical form. That's what the directions tell me to. And why would I want to do this? Why not do a decimal? Because decimals are rounded. It's not actually 14.9. Wasn't it 14.9 and it had a whole bunch of numbers? When you round, your answers are not accurate because you've cut some things off. So in order to be the most accurate as you can, you want to leave things in simplest radical form. So that's what we're practicing doing. So there we go. Okay? So sometimes you're going to have to reduce your radical. If you left it as 224, the square root of 224, that's fine. It's technically correct, but you need to simplify it kind of like what you do with fractions and reducing. So what you need to do is make sure you simplify it, which is why we practiced doing that in chapter 11.2 before we left school. Okay. All right, there we go. Okay, let's take a look at a couple more problems. I believe I have two more for you. Here. Now it's something more complicated. Take a look. Instead of whole numbers, I noticed that this side here is already as a square root. Interesting. But we can still solve these. So again, it's a right triangle. I see I have my two legs, right? This is a leg and this is a leg. So with my two legs here, we're going to call this A and B. Can I switch it? Sure. You can switch it. You can call this B and this A. It's up to you. But the one thing that has to remain is C, the hypotenuse. This has to be C. The hypotenuse is always C. And how do I know it's the hypotenuse? Again, it's opposite of the right angle. So let's put in my Pythagorean theorem. A squared plus B squared equals C squared. And we'll plug in the values. So A looks like X. So we'll write down X squared. We don't know what it is. B is the square root of 10. So let me write that down. Plus the square root of 10 squared, right? B squared. B squared. If you think about it, B I'm replacing with 10, square root of 10. And then C is 4, so 4 squared. So all I did was plug in the numbers based on my picture, my right triangle, and now we're going to solve this. Let's see. Are there numbers that we can simplify? I'm going to start with the easiest one, 4. 4 squared is 16, so I know that I can replace that with 16. And let's think about what this is. Square root of 10 squared. Doesn't that mean the square root of 10 times the square root of 10? Square root of 10 times the square root of 10, that's 100. And the square root of 100 is just 10. So look at all of that. When I simplify the square root of 10, it all just happens to be a nice number 10. I'm going to continue bringing stuff down. So the 16, I'm going to bring down. This x squared, I'm going to bring down. And there we go. So the key here is, I'm just going to highlight it. You need to make sure you're following your rules for radicals and being careful with your work, right? Squared means you multiply it by itself. 10 times 10 is 100, and that's a perfect square. So the square root of 100 is just 10. It's kind of nice, right? It reduces down to that. Now I'm going to continue solving it just like we did above. I see that I can subtract 10 to the other side because I'm trying to get x by itself. So we have x squared on this side equals 6. And then let's see, I have to get rid of the exponent 2. So I'm going to square both sides. The square and the square root cancel. So x is equal to the square root of 6. I wonder if I can simplify 6. Is there anything we can split 6 into? Can we divide it by 4? No. Can we divide it by 9? No. Actually, they're all too big. So square root of 6 cannot be simplified anymore. And there we go. That's it. I know that x, that side length over here in this picture, I don't know if you guys see it, this picture, is the square root of 6. Again, we are not rounding, so no decimals in this case. No decimal. Right? You leave it in square root format. The only time I might ask for decimals is maybe in a word problem, right? So you have to make sure you read the directions. But my directions here, if you remember from the very top here, I'll even scroll, was that I wanted you to leave your answer in simplest radical form. Your answer should be in simplest radical form. So that's what we need, okay? Okay, simplest radical form. So there we go. Okay, problem number 5, my last problem before I talk about cell phones. All right, here we go. Last problem here again. Ooh, interesting. So we see another another square root symbol here. So this is kind of trickier, but that's fine. We can deal with it. This is a leg, and this is another leg because they make up the right angle. So I know this will be A and B. And my hypotenuse is the letter C. So a squared, my Pythagorean theorem, a squared plus b squared equals c squared. Let's plug stuff in, right? For a, I'm going to replace that with 3. So this is 3 squared plus, and I like to do this. See how we have this term right here? I can put in parentheses just so that way you remember that it's this whole entire number squared equals c squared, which is x squared. So a squared plus b squared equals c squared. All right, I'm going to go ahead and do some multiplication now. Starting with the easy one. 3 squared, 3 times 3 is 9. So I know this is going to be 9. And then here, I'm going to show my work. We are multiplying, right? 3 square root of 3 times 3 square root of 3. That's what's happening here. When you square something, you're multiplying it by itself. When I multiply, remember, we multiply outside with outside. So 3 times 3 is 9 on the outside. And then on the inside, we multiply insides together. So that 3 times 3 is another 9. So many 9s. That's fine. Now, look, I can simplify this more. Square root of 9 is a perfect square. Doesn't this just become 3? So what I really have is 9 times 3. And 9 times 3 is 27. So that's all b squared. I'm just going to continue bringing stuff down. This was my a squared. So a squared plus b squared equals c squared. And I'll continue adding. 9 plus 27 is 36. And then the square root of 36, because I have to cancel my square and my square root. Oh, it's a nice whole number, 6, when you know. Lucky us, I don't have to do anything crazy. I don't need radicals sometimes. It's just nice whole numbers, 6. The newest Samsung Galaxy and iPhone Pro Max. Picture of it right here. If you take a look at any advertisement, anything telling you the size of the screen, Galaxy S20 Ultras, they say it's a 6.9 inch screen, and iPhones are 6.5 inch. They're slightly smaller, but what are they talking about? Because when they're doing this, they are not saying the height, right? So let me choose a better color. The height here in an iPhone is not 6.9. And the iPhone, the height is not 6.5. So why are they telling me in the advertisement that it's 6.9 and 6.5? If it's not the height, where are they getting these numbers from, right? So it's not the height. What is it then? Are they lying to me? No, they're not lying to you. What they're saying is that the diagonal, this from one corner to the other, this is 6.9. I don't know if you can see that. That's a horrible. Let me see if I can do it in a better color. 6.9. Not much better. Let me do it in white or in black. Yeah, there we go, I guess. Here we go. So this distance across is 6.9. So if you think about why that is, look, don't we have a right triangle right here? And they're talking about this diagonal length. That's 6.9. If you took a ruler, let me get a ruler out. If you could take a ruler and you measure the diagonal, that's 6.9. Same with the iPhone. The iPhone, the diagonal, this diagonal space here, let me see if I can do it in a color that you can see. Blue, sure, or green. This diagonal, this is 6.9. So this is 6.5, sorry, iPhones, not the height. So if you were to create a right triangle, right, if you create a right triangle, the diagonal is 6.5. And actually, I went and I looked it up. I believe the iPhone, if you took the whole entire iPhone, the height is actually 6.2 and the base is 3.1 inches. So the height of the iPhone is 6.2 inches, not 6.5. So if you're ever wondering, like, why are they lying to me in advertisement? They're trying to make it seem like it's bigger than it actually is. Because when they say 6.5, they're not actually talking about the height, they're talking about the diagonal, and it makes it seem larger. The height of the phone is actually 6.2 inches, not 6.5. So it's interesting when you go out and you look at like advertisements for TV screens or laptops or anything like that, anything that has a screen, and they advertise it as however many inches in the screen, they're talking about the diagonal length, which is the hypotenuse, right? They're actually talking about the hypotenuse, not any of the legs, not the height, not the width. So it's kind of interesting why they do that in their marketing, okay? To make it seem like it's bigger than it actually is. So anyways, there you go.